Hello. Hello, can you hear me?
Yes, I can hear you.
Great. Okay.
So everything is under control?
Yeah. Chauhanji is also here, so
That
it's
ISA
fine.
profile link is Chawanji, is it?
Yes.
Okay, wonderful. And you will be the host, right?
Yeah, I can be the host, and I will ask you to introduce the speaker.
Yeah.
And yeah, Massimo said he will join by in 5 minutes, essentially. So
That is fine. That is fine.
hi, Rahul.
Hi. So yeah, I was checking YouTube also. So can you say something? I check on YouTube.
Yeah, hi, hello. How are you doing, Rahul?
Mm, yes, yes. Okay. Yeah, okay, perfect. I think YouTube is also working fine.
Okay, great.
So this
Yeah,
will also
Massimo
be
said,
recorded, right?
yeah, it will be recorded, and Massimo said he will join in by 5:15, so should be okay.
Okay, so let's wait for him, right?
Yeah, let's do that. Yeah. Uh, Johan is calling me. Hello? Hi, Massimo.
Hello, how are you?
I'm fine. How are you doing?
Good, good. Thank you.
Yeah, let me first make you co-host so that you can share the slides.
Yes. Unable to start video. Oh, why? You can't start your video because the host has stopped it. Okay.
Okay. No, wait. That is bad.
Arnab, you have to give permissions, I think. I also see that I cannot start it myself.
Yeah, or you have to give permission or
So I think the host has to give permission to various people for uh, video. Audio seems to be automatic.
Yeah, can you now open your can you turn on your video? I think
No, Massimo still doesn't have video permission.
so Rahul, can you turn on your video? Is it? I mean, it should be same for.
let me try. Yes, I can.
Okay.
Yes, I can.
Yeah, okay, I can also. So I think it is possible. But then the issue is whether everybody can actually. But then Massimo should be able to do that.
Yeah. I mean,
Okay. I just collected my earphones.
yeah. Can you? Does it allow you to turn on your video?
Now I'm
Okay, can you hear me?
Yeah, I can hear you.
Oh, perfect. Second then. Okay, and now I try. Sorry, this earphone do not work for some reason. Why is that? Okay. All right. You see me?
Yeah, great.
Very good. Excellent. The only problem is that the earphone don't work well. For some reason, I can only hear on one side. Let me check that I have sound. Yes, there should be no reason why there is only one working rather than two.
Sometimes they're not very friendly with Zoom. I have seen the same thing actually.
Maybe I just put them back and try one second. They should respond.
okay.
Hello? Can you? Yeah.
No,
Yeah.
now I hear you through the normal from the Mac.
Okay.
So
So
maybe
how are things? How are things in Padova?
it's more or less. I'm back in the office, so I'm already happy about this. Yes,
Great.
we for a long time we could not. Well, we could come, but it was very few people were around. Now it's getting a little bit better. And there I hear it's really tough. It's a very tough.
It's at this point we cannot go to office. So
I imagine it's a very bad moment, right? It's a very
yeah.
I hope.
Ciao, Massimo.
Oh, hi, Eugene. How are you?
Hey.
Nice to see you. Nice to see you.
Welcome to India.
Right, we can meet virtually in this.
Yeah.
Korea, India, fantastic. Yes.
Right. Good. Very good.
Hello, Massimo. This is Priyatosh.
Oh, Priyatosh. Priyatosh, how are you?
I am fine. Let me. I do not know how put my video on. It's not getting on, I guess. Anyway, you can hear me at least.
Yes, absolutely.
I think Pritosh, everyone cannot put it on. Rahul.
Okay. It's okay.
No, at this point I enabled everyone actually. So
Okay,
I
let
think
me try
everyone
once again. No, but there is some, I am unable to. It's okay. I think we can just listen to him. So
I tried again with my earplugs because I can hear better.
now I can.
I see you.
Yes. Now I realize. Yeah.
Nice to see you. Nice to see
Yeah.
you.
Hope you come back to India soon.
Indeed. I would love to. I would really love to.
Okay, great.
Not so soon. I mean, after this COVID wave is over.
Sooner or later it will go away.
Yeah.
Do we want to try the slides?
Yes,
Yes,
let me just try once. Let's see.
Oh, connection is.
It's a problem with it.
Okay, let me stop video.
Let's see. Can you hear me now?
Yeah, I can hear you.
yes.
Okay. Very good. Now it works. Now it works on both sides.
Yeah. Should we start? Should we see if the slides work or?
Yes, absolutely. Okay, here it is. Let me start them. I prepared a few introductory slides, right? Because you told me that there would be many, perhaps students or.
Yeah.
Okay, so I try to start in a more introductory way. Let's see. Here we go. Let me start the keynote. All right, very good. And now let me share the screen. Keynote. Yes. Okay.
Yeah.
And I try to put it on
Full screen.
full screen. Does it work?
Yeah, it works fine.
Excellent. Excellent. I will put it back. I just check again with this earphones because it's a little confusing. This. Okay. Here. This I move on this side. This I make a little bit bigger. Okay. To the left. Okay. Excellent. I just close my door so that nobody comes in.
Maybe we start in a minute.
That's fine with me. Yes. Whenever you want.
हेही बंद करावं लागेल ना मला हे काढावं लागेल म्हणून
Maybe we can get started.
Okay.
So welcome everybody. Welcome. I welcome you all on behalf of Center of Forces in Nature, ISL Bhopal. This is a new center we started last year to study the various kind of forces that govern our world. So the first talk in this series in this center was given by Professor Michael Green sometime in October. Then we had another talk in February to celebrate our National Science Day. And today we are extremely glad to have Massimo Pasera from INFN Padova. We'll talk on muon G-2, which is a recent exciting development. So before I request Massimo to start his talk, I request Professor Rajiv Gabai to kindly introduce the speaker.
Thank you, Arnab. As Arnab mentioned, you all are aware that there has been a recent exciting news from Fermilab G-2 experiment. It generated excitement all over the world, including in the newspapers of Bhopal. We are really fortunate to have one of the greatest experts in this field to explain to us what it is all about. It is my great pleasure to introduce today's speaker, Dr. Massimo Pasera, who is Director of Research at the INFN Padova in Italy. After his undergraduate studies at Torino University in Italy, Dr. Pasera went on to the New York University for his PhD, where he worked under the guidance of one of the grand masters of electroweak interactions, namely Professor Alberto Serlin. After postdoctoral stints at Bern at Switzerland, Padova, Italy, Valencia, Spain, he finally joined INFN at Padova in 2005, where he continues to do his research today. He has actually visited several top institutions all over the world, such as Brookhaven National Lab at New York, Stanford, the Stanford Linear Accelerator Center at Stanford, Fermi National Lab in US, KIAS Seoul, and of course even our own Indian Institute of Science, Bangalore. He has several very well cited publications, including a 2020 physics reports on the very subject he will speak about. So let me not stand between you and him, and let us welcome Dr. Pasera to this talk virtually to India. Hope that he will come someday soon to India physically. Over to you, Dr. Pasera.
Thank you very much for this wonderful introduction and for the invitation. It would be really a great pleasure to visit Bhopal, in fact, when it will be possible. So thanks again. And as you said, we are here to talk about some news, important news. There has been an important measurement, new measurement in fact, a month ago. It will be tomorrow. It will be 1 month. It was April 7th, and when the Fermilab experiment, the muon G-2 experiment in Fermilab announced their new result, and that's why we are here. And the reason is that we have a difference, and there is a difference between the theoretical prediction, the standard model prediction, the model we have for particle physics, the best model we have for particle physics, and experiment. And so whenever there is a discrepancy, of course, we are excited. It's the moment to start thinking what can explain this discrepancy, which extension of the standard model could be responsible for this difference. Of course, it's also, as we have been doing for many years, we have to check and be sure that our prediction is correct. The prediction of the standard model is really the correct one. And and the experiment just confirmed from Fermilab the previous one. So we are on the experimental side, we are in very good standing. Let me just start mention a few words about, as I heard, maybe students who are at the beginning of their studies in quantum mechanics or field theory. Let me just remind everyone what we studied when we studied electromagnetism. We know that if we have a particle, it has a charge E that you see here. Well, just one question. You see my pointer, right? Is it? It is visible. Am I right?
Yes, yes, yes.
Perfect. Thank you. So, as I said, if you have just in classical physics, when you have a particle with a mass m and electric charge L, well, if it has an angular momentum, then this angular momentum generates a magnetic moment. And you see this formula that we all recognize here from our studies in electromagnetism. Well, now, and of course, this magnetic moment can interact with the magnetic field. Now, in 1925, so almost 100 years ago, two Dutch graduate students, Gottmik and Uhlenbeck, proposed that the electron has an internal rotation, characterized by a spin, and associated with the spin, they proposed a magnetic moment, like they were tiny, tiny magnets. And this is what they proposed. Here is the spin, and this is the associated magnetic moment. But as you see here, they they multiplied this quantity by a factor. We call it the G factor here. And this G factor, they postulated it to be 2, which is not 1. Okay, this is 1 is what appears in the classical relation between the orbital angular momentum. So this was really a surprise, but this was the number, G equal 2, was the number that was explaining the atomic spectra that were measured. This was 1925. It took just a few years. In 1928, Dirac wrote his famous equation, and that equation indeed told us that a unit of spin, of angular momentum, interacts with the magnetic field, in fact, twice as much as a unit of orbital angular momentum. So indeed, explained G equal 2. This was a major success, of course, of the Dirac equation, but it was only the beginning of the story, because in fact, a few years later, in fact, 20 years later, it took a while. In 1948, Cush and Foley measured a value of G, which was not equal to 2. What they measured was, you see it here, a quantity that we now call the anomalous magnetic moment, and is G divided by 2 minus 1, and it's not 0. Okay, G divided by 2 minus 1 is called A, the anomalous magnetic moment, and they measured it to be not 0. Okay, it's close to 0. In fact, as you see here, it is 0.001 and then other digits. But as you see, the uncertainty they had back then made it very clear that this quantity was certainly not 0. It's 119 with an uncertainty, and I will always use this notation in parentheses. When I write here 5, it's like writing 119 plus minus the last digit 5. This was clearly not equal, G was clearly not equal to 2, but in the very same year, in fact, Schwinger, using quantum electrodynamics, predicted the value that you see here. Alpha, the fine structure constant, which is roughly 1 over 137, divided by 2 pi, which gives you exactly 0.00116. So as you see, this is a fantastic agreement. You have 119 plus minus 5, and you predict 116. Major success of quantum electrodynamics. People, this together with the Lamb shift, of course, made people trust in electrodynamics. And this was the real beginning of the story of the electron and the later on muon G minus 2. So G minus 2 because G is not equal to 2. You see the diagram that Schwinger computed, this is a Feynman diagram, is the interaction of a muon. Okay, this is for a muon, but it could be the same for an electron in first approximation. First term of this perturbative series in alpha is the same, the contribution. And you see a muon or an electron interacting here, this point, with a magnetic field represented here by this photon. Now, the difference with the Dirac equation is that now we are in field theory. Quantum electrodynamics is quantum field theory. So you can now absorb and reabsorb here, emit and reabsorb a photon later on here. And the effect of this photon is, in fact, to shift the value from G equal to 2 to the value that you see written here. This is what we keep doing today, in fact, when we study the interaction of a lepton, so it can be an electron or a muon. The tau, unfortunately, has not been measured. And when you study the interaction of an electron and a photon, you see it like here. In a general form, we just put this red blob here to indicate the general interaction with the magnetic field. And in general, this, because of Lorentz invariant, can be written just in a few terms, and gauge invariance restrict them when this particle is physical, is on shell. The first term that you see here is a form factor we call F1, and this form factor is just that, of course, depends on the momentum q square, which is exchanged here. When q square is equal to 0, this is just the electric charge in units of E, as you hear. So in first approximation, it's just 1, and we keep it to 1 by the renormalization conditions. And F2, when q square, the other form factor that you see here, F2, when q square is equal to 0, is in fact equal to A, exactly what I defined above here. So the G minus 2 divided by 2, the anomalous magnetic moment. So this is what we need to do. We need to measure very precisely this quantity and then compare it with the prediction. And the prediction is obtained how? It's obtained taking a model. The model at the time was quantum electrodynamics. It's still quantum electrodynamics, but it's been extended. So you take quantum electrodynamics and you compute this particular contribution at q square equals 0, and you compare it with the experiment. This is what has been done for many, many years. And I would like to first just show very briefly what has been done in recent times in the Brookhaven experiment. The Brookhaven experiment in the years 2000s, it was, well, this is of course a very simplified explanation. Yeah, what was happening at Brookhaven was that you had the protons coming from the AGS hitting a target, producing the pions. The pions would decay into muons. And these are the muons, just the tiny magnets I was saying before, like spinning, like tiny magnets spinning on axis, like tops. And then they enter a magnetic field. You see it here in this yellow shape that you see here. And as they enter a magnetic field perpendicular, they of course starts to move on a circle. And at the same time, they have a spin, and their spin also precesses. And what you want to study is how the spin misaligns with the motion with the momentum of the muon. How do you do it? Well, you look at the decay of this particle. The muon decays into an electron and neutrinos, neutrino. So by studying these decays products, you will see what was the beginning, the spin of the particle, of the muon. This is the Brookhaven experiment. You see it here. And then in the 2013, it was wrapped in this, as you see here. It looks a bit like a spaceship here. It was wrapped and moved to Fermilab. So you see it went along the East Coast, then it went up the Mississippi, and this is in the St. Louis, and it reached Fermilab, as you can see here, going on highways for the last part. Very big move, it was called. And now it's here. It's at Fermilab, and it already took a lot of data. So what was shown a month ago was the result of the analysis of the first run 1. And this is it. This is the result of the Fermilab run 1 analysis to be compared with the Brookhaven one. And as you can see, the two are in good agreement. The Fermilab is a little bit smaller here, and you can combine these two to get the experimental average that you see here. So this is the measurement of A, the quantity A that I was saying just a moment ago. The index mu here means that it is for the muon. I will essentially only talk about the muon, except for a comment I will make towards the end about the electron. So this is the 0.001 that I was commenting earlier. The point is that now you see there are so many more digits that are known, and therefore it's convenient to multiply this number by 10 to the minus 10 or 10 to the minus 11. I will always use this times 10 to the minus 11. So you see this is the experimental value obtained at Brookhaven with this uncertainty 63, 10 to the minus 11. And this is the value obtained at Fermilab, run 1, 2089, and this is 2040. So they are in good agreement, and the uncertainties are written here. As they are in good agreement, you can just combine the two, and you get this new experimental average, which is has this tiny 41 in 10 to the minus 11. Notice this is a 0.35 ppm, parts per million precision. It's really an amazing precision. But it's only the beginning, because what has been collected, analyzed, sorry, in run 1, is only 6% of what is expected to be the expected data set that they will achieve at Fermilab. Run 2 and 3 are already completed. Run 4 is in progress, and there will be further runs. There is also another proposal for another experiment at J-Park in Japan, and its phase 1 is expected to have a precision similar to the Brookhaven one. So this is the experimental situation, as you see here. And now we have to compare with the standard model prediction, right? The standard model of particle physics. And this is what we have. We have a discrepancy. And the discrepancy is 4.2 sigmas if compared between the standard model and the experimental average. Before the difference was, the discrepancy was 3.7 sigmas. But thanks to the averaging and the good agreement between the two numbers, the uncertainty decreased, and now we have 4.2 sigmas. Now, let me go a little bit in the details to see if we can trust the standard model prediction. Let's see what went into the calculation of the standard model prediction. It took, of course, a long time. In fact, as you saw, it took 70 years, because the first calculation was done by Schwinger in 1948, so more than 70 years. All right, so just to be precise, when you will see this WP20, this is a number that I will quote from a white paper that has been written last summer in 2020 by the mu and G-2 theory initiative. It's a large number of people. In fact, it's roughly 1 over alpha, and this is was really an effort to try to produce the best theoretical prediction of the standard model to compare with the upcoming results from Fermilab. Let me start from QED, just as we started a moment ago. This is the diagram that Schwinger computed, and I already shown this very diagram a moment ago. This, of course, is only the very beginning. In this perturbative series, you see you have powers of alpha over pi, and here you have alpha over pi squared, alpha over pi cubed. Each step took, of course, an enormous amount of work. I mean, the first calculation was done in 48, and then the second one already in the 50s. And this is called one loop calculation. It's because you see there is one closed loop, as you see here. The two loop calculation is represented by the diagrams that you see here, and there are already several diagrams contributing at this order. You see, for example, here there are 2 photons instead of 1. And then 3 loop, and there are some diagrams of 3 loop that you see down here, but of course, many more. I'm only showing a few representative one. So we now know the 1 loop, 2 loop, 3 loop, 4 loop, and even the 5 loop contribution, which is an enormous amount of diagrams. And these are important. These are important because if you remember, and we should keep in mind this, what is the experimental uncertainty we have today? It's 41 in 10 to the minus 11, okay, 41. I will sometimes skip even saying 10 to the minus 11. I always take it for granted. So 41 is the experimental uncertainty. And now we are back here. So of course, these are smaller and smaller because the alpha over pi is linear, squared, cubed, 4th, 5th power. However, so you may think that it's how many loops do I have to compute? Well, look, the 4 loop contribution that you see written here is about 400 in 10 to the minus 11. So it's much bigger. It's almost 10 times larger than the present experimental uncertainty. So you need to know the 4 loop very well, and we do know very well, thanks to the work of very many people, in particular Kinoshita and his group worked on this for very many years, on 3 loop also as well, where also Emidi worked for many years. Stefano Laporta completed particularly part of this 4 loop calculation in 2017, which was an enormous effort. It took him many years to do this calculation. And then thanks again to Kinoshita and his collaborator, we now even know the 5 loop contribution, which however is pretty small. It's about 5 in 10 to the minus 11. So it's not so important for the mu G-2. It's important, very important for the electron G-2. But for the mu G-2, it's smaller than what we expect to be the predicted uncertainty that we'll have in the next 3 years from the experiment at Fermilab. Of course, if you want to compute the QED prediction for the G-2 of the muon, you need to compute all these coefficients, and that is what you see here. And then you need to plug in alpha. Okay, just as we did for the Schwinger calculation, where we need 1/2 was the calculation times alpha over pi. So what do you put for alpha? Well, alpha is measured directly, and there are in fact at present two different measurements of alpha, or better, they are very similar. But if you look at the uncertainties, which are claimed to be very, very small, there is actually a discrepancy between the two, which is significant. It's more than 5 sigmas. So you may be worried, which one should I take? It doesn't really matter for the mu g minus 2. As you see here, this is the value that has been obtained by the white paper last year, using this determination of alpha. This is the value of alpha from the Berkeley group in 2018. There is a new value of alpha, which is even more precise than this one, but it's, as I said, different, and it differs by more than 5 sigmas. However, if you just take the new value of alpha and you use it instead of the one from Berkeley, you will see that the shift is 10 to the minus 12, or the 10 to the minus 12. So it's very, very small. It doesn't affect at all the comparison with the experiment in terminal. So this is the prediction for the QED contribution. And as you can see, the uncertainties are really tiny. There are some small uncertainties here because this is a perturbative series and you do not know the next step. The next step would be the 6 loop calculation. It has never been computed. You can guess a little bit its size. And from this guess, you put this uncertainty here. You see, these are the last 3 digits. So it's like putting here a 1 here as an uncertainty, and this is therefore 10 to the minus 12. 10 to the minus 12 is very, very small, and it's not going to affect the comparison with the experiment. So the QED contribution is perfectly under control. This is, of course, just a subset of the standard model. It's just a subset where we consider only photons and leptons, photons and electron, muon, and tau. Of course, that's certainly not enough. Although this is by far the largest contribution, this is certainly not enough. So let's see what other contributions are important. Well, the electroweak contribution is much smaller, but it's of course very important as well, because you see, it was computed back in the 70s. You see, now instead of having a photon here, you have a virtual Z, okay? And here also you have a W, but then you have a neutrino here. So if you consider the diagrams contributing for the electroweak part of the standard model, you get a contribution at 1 loop order, which is 195 in 10 to the minus 11. And then if you add also the higher order corrections, you actually decrease significantly this value. And this is the best prediction we have nowadays, 153.6. There is an uncertainty also here, but this uncertainty is very small. And its origin is mainly due to diagrams like this one, where you have some hadronic contribution inside this weak contribution. I will come in a moment to the hadronic contributions, which of course the main topic nowadays. But let's remember that we have essentially no relevant uncertainties from the electroweak contribution, as you can see here. Okay, now we move to the hotly debated contribution, which is the hadronic contribution. You see, the hadronic contribution is this diagram here for the leading one, is described by this diagram. Here is still the same diagram that you had with the emission of a photon and we absorbed here, but now this photon here has a bubble inside where you have hadrons. Now, this, of course, is a complicated contribution because how do you compute this hadronic contribution? Here you have, inside this loop, you have momenta of all sorts, so you cannot rely on perturbative QCD, quantum chromodynamics. You have to think of something different. And in fact, the solution is well known. It has been known for decades. Why? Because we know that this bubble here that is called vacuum polarization, this vacuum polarization in particular, this is the hadronic vacuum polarization because it's the one containing hadrons. The one containing leptons is already described in the previous part of what I said. Now we have hadrons inside here. So this function is analytic. As this function is analytic, we know it has a cut on the real axis. So we know how to compute the full function if we just know the imaginary part of this function along the cut. How? Well, we just use a dispersion relation. Dispersion relation allows you to get a full analytic function just by knowing its imaginary part along the cut. This is what we need. So therefore, we need the imaginary part of this vacuum polarization function. It's called hadronic vacuum polarization function. And how do we get this imaginary part of the vacuum polarization function? We get it from data. In fact, there is the optical theorem that relates the imaginary part of this vacuum polarization to a cross-section that can be measured. And this is a cross-section of initial state E plus E minus into a final state. And the final state is any hadronic state that I can consider in this bubble. So we really need to study E plus E minus into hadrons. Of course, you wonder immediately, well, at which energy do I have to compute this cross-section? Well, at any energy, but then which one are relevant for this calculation? But to know which one are relevant, you need to write this contribution. You see it here, hadronic, leading order contribution to the G minus 2. And as you see here, just because of what I said, you have to do a dispersive integral, use a dispersion relation. You have to integrate over all energies from the minimum possible one, which is the minimum state that you can, minimum energy state that you can have inside this bubble, which is a pi zero and a photon. So for example, this could be a pi zero and a photon here, and up to infinity, the maximum energy. So you need this cross section everywhere from all energies, from the square root of S equal to the mass of the pi zero up to infinity. However, as you see here, this integral has a kernel in front. And this kernel, I didn't write it explicitly because it's a bit long, but I wrote it in integral form here. And this kernel function, k of s, roughly goes like 1 over s for large S. So it really gives a lot of weight to the low S region. So you really need to measure the cross-section precisely at low S. Well, in fact, when you're at very high S, you can actually use perturbative QCD. There you can trust perturbative quantum chromodynamics. Now, the problem is that to measure something so precisely is difficult, because how much precise, what is the precision that you need? Well, it depends on how large this contribution is. And this contribution, as you can see here, is about 7,000 in 10 to the minus 11. As the experimental uncertainty is about, of the G minus 2 is about 40, well, you see that you need to know this number at better than 1%. 1% would be 60 or 70. You need half of that. Well, in fact, this has been obtained. And in fact, you see these are three determinations from the groups that worked a lot on this, Prediger Elena, in fact, and the group of Michel Davier, Herker, Malesco, and Chang, and the group of Keshavarzi, Nomura, and Teubner. These three groups worked for many years producing updated values for this determination, and the results they have are in agreement, as you can see here. Of course, the uncertainties are much bigger than the uncertainties we saw earlier for the QED contribution and the electroweak contribution. These are dominating uncertainties that you see here. In red, you see down here, this is the merged value, the value quoted by the white paper I was telling you before, a merged value of the previous values here. It has been merged conservatively and obtained adding constraints, analyticity and unitarity constraints from the group of Colangelo, Hoferichter, Freud, Kubis, and Bastian Kubis, and Peter Stoffer. Of course, you see here, this precision is very high, it's 0.6%, and this is what is needed, because this 40 is really the same, very similar to the 41 that we now have from the combined Brookhaven and Fermilab experiment. It's a conservative uncertainty, the one that is quoted here. For example, this is bigger than the one that you see here. Of course, it takes a lot of work to estimate this uncertainty, because many ingredients go into this, and you have to control the radiative corrections, of course, to the hadronic cross-section at the level of better than 1%. There is a report written here several years ago that summarizes the work that has been done for many years on these radiative corrections. Let me just show you the many channels that enter in this determination. So here, really, we are using data, experimental data, E plus E minus into hadrons, to determine a theoretical contribution, the leading hadronic contribution to the muon G minus 2. And here in this nice pictorial way, you see the several channels that appear, because when you say hadronic state, what do you mean? Well, the leading one is this one in yellow, and it's the pi. So E plus E minus into pi plus, pi minus. And notice that this is a log scale. So as it is a log scale, of course, this contribution is very important. And at low energy, it's by far the dominating one. This one, for example, is the one that I was mentioning. This is a plus E minus into pi zero and photon. But there are orders of magnitude here, you see. So this one is really much, much smaller. When the energy of your E plus E minus collision increase, Then you start developing many possible final states, and here you have you see many of them. In fact, it's not even all of them. You even have more than 30 channels that contribute to this determination. And here is a focus on the pi channel obtained by many different experiments. Now, on the very same day of the announcement of the Muon G-2 by Fermilab, Nature published an important result by collaboration, theory collaboration. It's called the BMW collaboration, where the authors have done a calculation using lattice QCD. So this is a real calculation of the theoretical calculation of the leading hadronic contribution to the Muon G-2, starting from first principle. This is QCD. They are not using data. Okay? They are really using lattice QCD to obtain this result. And this result, you see it written here, is actually different from the one that I showed you a moment ago. So the one that I showed you ago, let me go back. This one I will call the dispersive determination because it involves the dispersion integral that you see here and the plus and minus data. The one that is here on the contrary is obtained from the lattice. This is the plot taken from their paper. So you see here the dispersive determinations.
In fact, this paper came out already some time ago. Oh, can you still hear me? Because my ear plug.
Yeah, we can hear you.
Crashed. Okay, so you see, these were the determination that were obtained on the lattice before, and their uncertainties were larger. As you can see here, these are the error bars, and they're significantly larger. But then, thanks to this really amazing effort that was done by the BMW collaboration, in fact, a year ago, in February 2020, they managed to come up with this beautiful, amazing result. I mean, a lattice calculation, so first principle QCD calculation with a precision which is better than 1%. In fact, it is 0.8%. And you see it here. Now, in this plot, you see in this figure, you see here, these are the dispersive determination. These are previous lattice determination with larger errors. This is the BMW determination with a very small error. And in this blue line that you see here, this is what is needed to fix this is what is needed to reach the experimental value. So as you see here, the discrepancy here is large, and as I said, is 4.2. Well, this was compared to the Brookhaven one. So at the time, this was 3.7 sigmas, but doesn't matter. This was the discrepancy before between dispersive result, standard model, dispersive result, and experiment. But now the BMW determination is much closer to the experimental value. In fact, the discrepancy is now just 1.6 sigmas. On the other hand, there is now a tension between this lattice determination and the dispersive one, of course. And this is around 2.5 sigma, as I write here. Depends which one you take. It's 2.2 with respect to the white paper. How to clarify this? Well, what is really needed here is a confirmation. And so this result has to be confirmed or refuted by other lattice calculation. This is the first, the BMW one is the first result obtained with such a high precision on the lattice. It has to be confirmed or refuted by other calculation. It's a very important result, of course. It's just a few years ago, I would have imagined that it would have been extremely difficult to go to below, to reach a precision better than 1%, but this happened, 0.8%. Let me just mention very briefly that there are higher order contribution. They are in very good standing. You see them here. You have an additional photon here. They are well known. They have been computed by Krause many years ago and perfected by many groups. And this is the value of the white paper. There is even the contribution at next reading order from vacuum polarization is written here. And it's a bit bigger actually than what was expected, but now it's perfectly known. It's computed. The last contribution I want to mention is the hadronic light by light contribution. So you see here, this is, again, it's a high order contribution, so it's small, but it is a very difficult object because here you have a 4-point function. You see 1, 2, 3, 4-point function. It has been computed by models by many groups. It had a really troubled life. It even changed sign, but these are the numbers of groups that worked a lot on this in the last few years. And this is the white paper number that appeared last summer. Notice that the uncertainty of this contribution is much smaller than what it used to be. And why it is smaller? It's smaller because there's really been a significant improvement here. And the improvement has been due to the data-driven approach, dispersive approach that was introduced by the group in Bern and in Mainz. As you see here, these people worked a lot on this determination, and they managed to produce such a very precise determination. So what in the past was really a problem, because we always thought, well, what will we do in the end of this hadronic light-by-light contribution? It will be a showstopper. We will never be able to gain and take advantage of the precision that will be reached by Fermilab. Well, this is no longer a problem from the light-by-light contribution, because it is really very precise, as you see here. In the meanwhile, by the way, there has been, this is another very important achievement. The lattice community attempted a calculation, and they managed. You see, they managed to compute this 4-point function on the lattice, and they obtained this value here in 2019 in November, and on April 7th, this new determination with this extraordinarily precise value that uncertainty that you see here. So these values are really making us safe that the discrepancy that we see in the standard between standard model and the standard model and the G-2 is not due to the presence of to some problems in the light-by-light contribution. We even know the higher order light-by-light hadronic contribution. We estimated it a few years ago. It's a small contribution, and the uncertainty is negligible. So if you put together all this, as you see, this is the experimental value. This is the standard model prediction from the white paper. As I say, the white paper is the one, as I said before, the white paper one is from the dispersion relation. The result from the BMW is not included in this determination here. And the difference, as I said, is 4.2 sigmas. This is not taking into account the latest result by the BMW determination. Now, this is a large discrepancy. Now the earpods start working again. Let me turn them off. Just 1 second. Sorry. In these units, this is, as you see, 250 and an uncertainty of 59 when you combine everything in quadrature. And so, of course, it's a perfectly good moment to start thinking, what is the new physics that can, beyond the standard model, that could explain it? And of course, in fact, immediately after the result at Fermilab, many papers came out with new ideas, with older ideas, and I mean, it has been an explosion of on the theory side. This will be a completely different talk. Let me just mention that, of course, we have a number, right, to compare. So that's it. We only have a number. So of course, it could be very many possibilities, but we have to see whether they are compatible with all other measurements, experimental measurements that we have. So it could be some new physics at the weak scale, in which case it would be need to be weakly coupled to the standard model, or it could be heavy and strongly coupled then, or, and it's very popular nowadays, some very light new physics, so with very, very tiny, feebly coupled to the standard model particles. I will not really talk about this. I will devote the next 10 minutes to a different question, however, which is an important question right now, I think. And the question is, could it be that this discrepancy is not due to new physics, but is due to a mistake in the calculation of the hadronic contribution, and in particular of the leading hadronic contribution? As I mentioned, it's really the light-by-light hadronic contribution is in very good standing. So or at least it's in good standing and not sufficient. The uncertainty in any case cannot explain this 250 that you see here. So a question that we asked, in fact, together with Alberto Sirlin and Bill Marciano a few years ago, was a connection with delta alpha, that is the running of the fine structure constant, right, from 137 to different values. So let me explain what I mean by this. What I mean is that it could be, and we take for a moment, consider seriously the possibility that the hadronic contribution is wrong. And it is wrong. Why is it wrong? Well, we assume that the leading hadronic contribution is wrong because the input, the experimental input that it uses is wrong, is incorrect. There is the standard, as I told you earlier, it's based on the experimental data that enters is the hadronic cross-section, E plus, E minus into hadrons. It's a positive contribution, the one that you obtain. The leading hadronic contribution is a positive contribution. And as the experimental one, let me go back here. You see the experimental value is bigger than the standard model one. You need a higher leading hadronic contribution. So you need a higher cross-section. So could it be that this cross-section is smaller just because we missed some contributions in this in the measurement? So the question is, could there be some missing contribution in the hadronic cross-section? So what you need, it would be to shift up the hadronic cross-section, and then you could fix the G-2. Some experimentalist friend could come tomorrow and tell us, look, in that particular region, we missed a contribution, and thanks to this contribution that now we measured and before we did not, now we have perfect agreement between the prediction of the mu G-2 and the experimental measurement. It's possible. Yes, it is possible. Of course, it's a possibility we have to consider. But let's take it seriously. If you really think that there is a change in the hadronic cross-section here, well, then something else also changes. And the something else is this other integral that you see here. See, the first integral is the contribution to the leading hadronic contribution to the mu G-2. But the very same cross-section, sigma hadronic, I didn't write hadronic, but the same cross-section, enters also in this other integral, which determines the running of alpha, due to the hadronic contributions. The kernels that you have in front are very different, however. Although the experimental input is the same, the kernels are very different. You see, in this case, the kernel is the function k that I showed you earlier, roughly going like 1 over s for large s. And here, this g, on the contrary, well, is written here. It depends at which value of q squared you compute your delta alpha hadronic. If you compute it at the mass of the z squared, well, then you see the mass of the z down here and up here. So this function for small values of s, let's say s around 1 GeV, well, this is essentially a constant. So this is essentially a constant, and this is roughly like 1 over s. So there are very different kernels here between these two. So let's, as I said, take seriously the option that the cross-section sigma has to be increased. So we increase it by multiplying by this epsilon coefficient here, epsilon times sigma of s. Where do we do this increase? Well, we choose to do it in a certain bin, a bin which is centered at square root of s naught that you see here, and as a width, which we call delta. Well, so if we have this bin, we change the hadronic cross-section to fix the G-2 discrepancy, but then we also change delta alpha at mz. Does this have consequences? Yes, it does, because delta alpha at the mass of the z is one of the key ingredients of the electroweak precision tests. So let me just give you one slide for this. Back when we did this exercise, it was in 2008, the Higgs boson had not been discovered yet. As you know, it has been discovered in 2012. However, in the standard model, you can compute and predict quantities which are related to each other. So you can predict the mass of the Higgs of the standard model from other measurements, comparing, for example, the prediction of the mass of the W, which you can compute very precisely, and comparing it with the measured value of the mass of the W. It will depend on the mass of the Higgs. So you can solve for the mass of the Higgs and see what is predicted by the standard model. Among the inputs that you have to use, there is, as I said, the delta alpha hadronic at the mass of the Z. So as you are modifying this input, you're also modifying the prediction for the mass of the Higgs. So the exercise we did back then was the following. What is the upper bound? At the time, this was the most interesting thing to show. What is the upper bound on the mass of the Higgs that you can obtain from the standard model? And the prediction at the time, in 2008, was this one, to be consistent with all the other measurement, precise electroweak measurement, the mass of the W, the Weinberg angle, and the other parameters. So if you measure everything and compare with the precision prediction of the standard model, back then, we had this upper bound on the mass of the Higgs. The mass of the Higgs had to be at most 150 or 160 GeV. Nowadays, we know that the Higgs is right here, 125. But at the time, we didn't know. We only knew this upper bound from the electroweak fit. We didn't know the mass, but we knew a lower bound because LEP had not discovered the Higgs. LEP, the previous experiment before LHC, had not discovered the Higgs. So LEP could say that the Higgs, if existing at all, would have been heavier than 114. So this region was excluded by LEP, and this region was excluded by the electroweak fit. Now, As I said, the electroweak fit uses delta alpha as an input, but now if you change delta alpha to fix the mu on G minus 2, this black upper bound moves into the red line that you see here. So including this information from the G minus 2 changes very much the upper bound from 150 to 50, 60 GV to this red line that you see here, which, however, is not a flat line. It depends on where you change your hadronic cross-section. If you change it at low energy or at higher energy. This is 1 GV, by the way. 1 GV is right here. So as I said, we didn't know the mass of the Higgs back then, but we already knew that the mass of the Higgs could not be lower than 114 GeV. So already back then, already 10 years ago, we could conclude that it cannot be that some experimental colleague comes and tells us, look, there is a problem. The mass, the hadronic cross-section has to be increased at, say, 2 GeV. No, because if you increase the mass of the hadronic cross-section at 2 GeV up here, then the upper bound on the Higgs would have been completely in conflict with the LEP lower bound. So yes, it's possible to change the hadronic cross-section. It's possible that there is some missing contribution, but this has to be at low energy. By low, at the time, we could say below 1.5 or 2 GeV. We redid this analysis thanks to the push of Alex Keshavarzi, who was very good at pushing us to redo and update this, because many things change. In fact, as I said, now we have the Higgs mass. The Higgs mass is this line that you see here. It's a very precise measurement. The uncertainty is actually there, but you cannot even see it because it's a very narrow, it's 140 MeV, and these are, you see GeVs here, so you cannot even see the uncertainty here. So this again is the MH prediction from the electroweak fit, and this is where you change the cross-section. So if you change the cross-section, you get the central value for the MH prediction, that is the central line here. You see steps if you do it in steps, you see a line if you do it in a narrow peak. The orange is plus minus 1 sigma, and the pink is plus minus 95% confidence level. So as you see here, if you go above, say 0.7 GeV, roughly 0.7 GeV, well, then you have a conflict between what is measured for the Higgs mass and what is predicted by the electroweak fit at 95% confidence level. Of course, you can be more restrictive. You can go to 3 sigmas, and then it's a bit higher. It would be up here. The upshot is, yes, you can change the hadronic cross-section to solve the G-2 discrepancy, but you cannot do it at high energy. You have to do it below 1 GeV, because if you do it above 1 GeV, you solve the mu and G-2 problem, but you screw up the electroweak fit. So you just move the problem from the G-2 to the electroweak fit. Let me comment that, therefore, the electroweak fit, you can still think of doing this exercise of changing the hadronic cross-section below 1 GeV. If you do it below 1 GeV, there is some tension, but the electroweak fit is not strong to say that you cannot do it. So we thought about the possibility of doing it below. And then you wonder, however, by how much do we have this to change this cross-section to fix the mu and G-2? And this plot shows you exactly that. How much do we have to change this hadronic cross-section to fix the mu and G-2? Where? Well, we are assuming now a bin starting from 0 up to a certain value that you see written here. Let's say that we take, for example, a bin from 0 to 1 GeV. Now we change the cross-section in this bin and we fix the mu and G-2. How much is this shift in the hadronic cross-section? This is what the blue line is telling you. It's a shift of 5%, roughly 5%. If you do the shift from 0 to infinity, which of course it has no meaning, of course, to change the cross-section everywhere, well, still you get a minimum which is 4.1%, and it is this dotted line that you see here. Are these numbers large, or is it this change of 4% or 5% or 8% if you go down here, large? Well, yes, they're actually large, because the experimental uncertainty that you get from the same range, for example, integrating from 0 to 1 GeV, the experimental prediction, the experimental measurement has an uncertainty of less than 1%. So you can do the shift above one, you cannot do the shift above 1 GeV, because roughly 1 GeV, because then you have tensions with the electroweak fit. But also if you do them below 1 GeV, you have a problem because you have a conflict with the quoted experimental precision, the experimental precision quoted by the experiments. This is literature related to the same analysis, similar analysis, connecting the mu and G-2 with the running of alpha, delta alpha, in the last year. And let me just say 2 words on the electron G-2. The electron G-2, I did not mention it till now. The situation there is a bit messy because you see what was done for many, many years for the electron G-2 was not to use it as a test of the standard model. What was done was different. It was done to obtain alpha. So 1/137 that you see here was in fact obtained from the G-2. How? Comparing the standard model prediction, which depends on alpha, to the experimentally measured value. For example, this is the value that you get from the best measurement of the electron G-2 and the best theory calculation of the electron G-2. You get this value of alpha. This is the value that appeared in the particle data book for several years with some modifications. Now, what happened in 2018 is that actually alpha was measured independently from atomic interferometry. So this is a measurement, and with very high precision, in fact, better than the one that you can obtain from the electron G-2. You see the precision that you can get from the electron G-2 right now is this one here, 0.24 parts per billion. Okay, this is a billion, okay, parts per billion. But if you do it directly, measure a direct measurement of atom interferometry, you get even better. And this was the measurement I was telling you at the very beginning. It was done at Berkeley in 2018, 0.2 parts per billion. Now, as I mentioned at the very beginning of this talk, actually just before Christmas in 2020, there has been a new fantastic measurement in Paris of alpha with even better, even higher precision. But unfortunately, these two numbers are not in agreement. Not at all. In fact, they have a disagreement of 5.4 sigmas that you can see very well here between this and this. This is alpha measured directly in Berkeley and in Paris. As you can see, they are different, and the discrepancy, as I mentioned, is 5.4 sigmas. This is the prediction comparing the standard model, the value obtained matching the standard model prediction and the electron G-2. So unfortunately, we cannot really say what is the standard model prediction of the electron G-2 because you have two different inputs, or better, you have one input, which is alpha, but it has two measurements which differ too much, and you cannot take an average of these two. You can only get two separate numbers from this, and therefore two discrepancies from the experimental value. And they even change the sign. So really, unfortunately, we cannot say much at the moment. This situation has to be clarified. It's a pity because, as we pointed out several years ago, together with Gian Giudice and Paradisi, this is actually, once you have alpha and at this level of precision and an improvement which is expected on the direct measurements of the electron G-2, there is no issue from the theory. The theory is ready to do a test of the standard model from the electron G-2. And more importantly, you could even check, well, more importantly, it's actually the same thing. You could even check if the discrepancy that we see in the muon G-2 also shows in the electron G-2 by scaling it. This is a scaling that we call naive scaling, which occurs in a broad class of BSM theories. And you see it written here, the mass of the electron, the mass of the muon, for example. So you can just rescale the discrepancy of the muon G-2 and obtain this, in naive scaling, a discrepancy for the electron G-2. And it is of the order of 10 to the minus 13. And 10 to the minus 13 is really only limited, as you see, the uncertainties are theory uncertainties are much smaller. It's 10 to the minus 14. So they are not a limitation. The point is that we need a better measurement of the G-2 itself, electron G-2, and the input delta alpha should be, of course, there should be no disagreement between measurements. So this is what hopefully will occur soon. There is no issue if one shifts the hadronic cross-section, as I mentioned earlier, to fix the muon G-2 in the electron sector, because this is a tiny shift. It's order 10 to the minus 13, so it is really not an issue. Let me mention, if I still have a few minutes, is it okay if I have like five more minutes?
Sure.
Okay, let me just mention a proposal for a new experiment that I would like to introduce to you. This is a proposal for a new experiment at CERN to actually get the leading hadronic contribution to the muon G-2 in a completely different way, in yet another way. It's not the dispersive way, it's not the lattice QCD, it's a different one. It's called the Muoni Project. And the idea is the following. Together with Carlo Carloni Calame, Luca Trentadue, and Graziano Venanzoni, several years ago, we were wondering, So this is what is done, the leading hadronic contribution. It is what I showed you already earlier. You see the input here, the dispersive integral done on the hadronic cross-section, the plus and minus into hadrons, as I said already several times. Now, we wondered, could it be that, you see, to get this result, you have to combine more than 30 channels here, so more than 30 measurements from different experiments. It's really very difficult to include the radiative corrections at the level of better than 1%. So it's really a very challenging proposal. And I mean, not proposal, it's been challenging work to do, and this has been done, but it's very difficult to decrease the uncertainty of this contribution. So in fact, if you look at this formula, there is an integral here, and then there is another integral here, which is written here. Now, if you just switch these two integrals that you see here, so you first do the integral over S, and you keep the integration for x for afterwards, for later, you see that you get a different expression, an expression that you see here with another kernel. Now the integration variable is x, is no longer s. And you see there is a kernel which is 1 minus x, and then there is delta alpha here, the running of alpha. The running of alpha, where? Well, at a value of q squared that we called t. We called it t because this value of q squared is negative. So actually, we certainly didn't derive anew this formula. This formula is long known. It was computed by these people in the 70s. And this is the formula, by the way, practically, this is the formula that is used by the lattice colleagues. But this is exactly the formula that was answering our questions. Can we do one, instead of using so many different experiments, can we do one single clean an inclusive experiment to determine the leading hadronic contribution to the mu G minus 2. And in fact, this could be perhaps the right way to answer these questions, because what you need to do, what this formula is telling you, is that you need a scattering experiment. You see, a scattering experiment like the one I'm showing here, where delta alpha is the hadronic contribution that appears here in the scattering and in the T channel. You see, it's a T channel because you have a variable here that is T, which is space-like. So it is a Q square, which is negative. So it's a T channel process. So we started thinking about a scattering experiment. Instead of doing a plus and minus into 2 pi, 3 pi, 4 pi, and so on, we thought of something very clean to do, like E plus and minus into E plus and minus, purely leptonic process, where, of course, then you have to measure very precisely the vacuum polarization that is appearing inside this blob. Right away, we thought E plus and minus into E plus and minus, as I told you, that is Baba scattering, of course. And but that looked very difficult to accomplish. We thought that the better solution would be to do a fixed target experiment, that is scattering muons on a fixed target on the electrons of a fixed target. So doing muon electron into muon electron, mu e, elastic scattering. So is it possible? Well, the wonderful thing we found out is that there is a beam at CERN. It's an intense muon beam at CERN with an energy of 150 GeV, which is there. It has been used for many, many years. It's in the north area at the center of the LHC ring. And so we did this proposal to scatter muons from this beam against targets and then measure very precisely the scattering. You see it here, electron recoiling and muon recoiling. How do we do the measurement? We measure very precisely with these thin silicon strips that you see here. We measure very precisely the differential cross-section. In fact, what we need is only a shape that we need of the differential cross-section in normalization region and in signal region. We need to put many of what we call here stations. We cannot do just one and measure very precisely, because then this target would become too thick. And if the target is too thick, then you have a lot of multiple scattering and you cannot get the electron out without doing all this multiple scattering, and that ruins the measurement. So we decided to actually split the target into several targets and therefore do many of what we call here stations, many stations. Each station has a target and has the silicon strip detector that you see here. We repeat this many times, in fact, something like 40 times. And at the very end, we also put an electromagnetic calorimeter here, and which also gives particle ID between muon and electron. This is what we proposed. This is the integral that you see here. You see the integral is 1 minus x times delta alpha, or better, the integrand. Let me plot the integrand. The integrand is the curve, the red curve that you see here. Of course, now we have no spikes. There are no thresholds here. This is Euclidean, right? This is the negative space-like region. So it's a smooth function, very smooth function. And we would like to measure this function, to populate with points this. Can we cover, how much of this region can we cover it? Of course, we cannot go up to x equal 1. X equal 1 would be infinite energy. We cannot have infinite energy. But with 150 GeV muons, we can actually go all the way up to the blue line, blue vertical line that you see here, which is a good fraction of it. It's actually, there is only a 13% missing here. So coming back to our initial proposal to get most of the determination, well, we can get most of the determination of the leading hadronic contribution to the mu G minus 2 via this measurement, if we can do this measurement. By the way, this missing strip is not a problem at all. It can be obtained using the usual time-like approach, dispersive approach, or by a lattice QCD. In fact, it has been computed by this gentleman in the Giusti and Simula and by Marinkovic and Cardoso. So with this missing piece is not a problem. For us, you see, we have really a nice interplay between a region where we have the signal, where we have the hadronic contribution, and a region where the hadronic contribution is small, and so we call it the normalization region. So that's why we need only a ratio, in a sense. We need only the shape of the differential cross-section. Otherwise, it would be extremely difficult. It's already extremely difficult, but it would be even more. Let me conclude just mentioning that from a statistical point of view, we would need 2-3 years of running, and then we could reach this integrated luminosity. And from a purely statistical point of view, this integrated luminosity could give the leading hadronic contribution to the mu G minus 2 with an uncertainty of 20 in 10 to the minus 11. So 0.3%. 20 in 10 to the minus 11 is 1/2 of what is quoted today by the white paper. Of course, I'm not claiming that we can do this. This is what we could do statistically, but then of course there is the systematic effects. The systematic effects are extremely difficult to control. We need to control them at better than 10 parts per million, which means 10 to the minus 5. So we started doing test beams. We did 2 of them, 2017 and 18, and they are actually encouraging. And as they were encouraging, we submitted a letter of intent to CERN SPSC in 2019, and it was approved for a test run that will start in October. We will have a 3 weeks test run this October, and then we will see what we get from this test run. If everything works fine, and it's a big if, of course, then we could start producing the full experiment and running it for 2-3 years in the following years. As I'm a theorist, let me mention that you need 10 ppm in the experiments for Muoni, but therefore you also need 10 ppm in the theory. And this means that you need to know all these effects. I mean, you need to predict the standard model, the shape of the standard model prediction at 10 ppm, which is extremely difficult. And we started in 2016 and 17 doing this. We have a prediction at leading order. We have a prediction at next to leading order with a fully differential Monte Carlo developed by the Pavia group and the PSI group in Switzerland. We are working here in Padua under the coordination of Pierpaolo Mastrolia. We are working on the QED 2-loop contributions, and the result is really close to completion. There are already 2 Monte Carlos which include partial subsets of the next to next leading order QED contribution. This will not be sufficient. We already know this. We had to compute also the hadronic effects at next to next leading order because they have to be subtracted out. Otherwise, they will mixed together with what you want to extract. And well, there are many issues that we described in the theory. We have our own Muoni theory initiative, and we wrote our white paper here in this article that you see here. We even looked at the possibility that new physics affects the extraction of delta alpha, but apparently this is not an issue. We hope that this will develop in the next few years. Let me come to the conclusion. I hope that I convinced you that we really have a beautiful interplay here between theory and experiment in the mu G minus 2, but also in the electron G minus 2. And this actually involves different areas of physics, as you saw. Specifically for the mu G minus 2, we have beautiful results from Fermilab. just very fresh new results. It confirms the Brookhaven one and increased the previous discrepancy of 3.7 sigmas up to 4.2 now, 4.2 sigmas. On the other hand, there is this recent lattice result that I told you about, the BMW result for the leading hadronic contribution to the G-2 that weakens this discrepancy, and it weakens it significantly down to 1.5 sigmas. So clearly now what is needed is new determinations on the lattice, same thing, lattice determination to confirm or refute this important result. I mentioned the possibility that instead of being new physics, the explanation between these two, the explanation could be some missed hadronic contribution, miscontribution in the hadronic cross-section. This is possible, but it should not be above roughly 1 GeV, because if it is roughly above a square root of S of roughly 1 GeV, then you solve the mu G-2 discrepancy, but you have a conflict with the electroweak fit. And finally, well, I mentioned this new proposal at CERN, which is complementary to the dispersive and the lattice one. We really hope that it will work. And in fact, it's in a phase where people interested, we would be very happy if people are interested. Please just contact us. We are in a phase where everything is still new and we have to work both on the theoretical side and on the experimental side. So any help would be greatly appreciated. Thank you very much. I will stop here.
Thank you. Thank you very much. So do you have some time to get some question? Yeah.
Obviously.
Okay, so is there any question from the audience?
Can I ask one?
Yes, please.
Thank you, Massimo, for a fantastic talk. Very, very well done.
Thank you.
My question is actually related to two things. One is the one which you talked about as your point number 4 in this slide, and the next is on the point number 5. Let's stick to point number 4. Now, can we go back to the place where you show that a 2.5% change in the cross-section does something to BMW?
Yes. Yes, in fact, you mean this plot here, right?
Exactly.
Yeah,
sorry,
I didn't comment on that. I'm sorry. Yes, I didn't comment on the red line. Absolutely. So what is your question? A comment on this thing, right?
Yeah, so my question is basically that if one wants to make agreement with BMW, then BMW itself is at 1 or 2 sigma away from the experimental physics. So
Yes.
in that sense, much less shift is needed.
Exactly.
And then going back to the experimental cross-sections that you showed, how feasible is this particular shift in the data in the region up to 1 GeV?
Well, you see now, indeed, this is a sort of intermediate situation. This is certainly a large shift. This tension is less because, as I said, so the tension between, if we take the asymptotic value here, meaning a uniform shift, which of course doesn't have a meaning, but I mean, the overall discrepancy between BMW, and this is the updated value of BMW, because the previous version was a bit higher. Now this is the published value that appeared on Nature. So if you take this one is 2.1%, the shift on the cross-section, and the tension is only 2.2 sigmas, if I remember correctly, with the white paper prediction, so with the dispersive result. So it's not easy to make some strong statement here because we are in an intermediate region here. So really, while here, of course, we can make such a strong statement, here we are in the middle. It's more difficult to say. On the other hand, this is still large. I mean, 2.1 is still, well, large. It depends on, the number is 2.2 sigmas. That's it. The overall number is that. Of course, if you restrict to smaller ranges, then you see that the percentile increase, if we restrict to the region between 0.7, 0.8 that I was mentioning above, this increase is higher, as you see here. But indeed, with the BMW, as I said, the tension is much less because BMW is really more in the middle. So I cannot say much more here.
And in terms of the existing data in this region, is
Yes.
such a shift possible in the sense that the low enough energy, so all hadron calculation may not have, I mean, something would have been missed by them, and the cross section is in some sense lower bound on what should really be in the measured one.
Sorry, please. I missed you for a moment at the beginning. Sorry, if you could.
Can we go back to the total cross sections that you
Yes.
showed at some point?
Actually, yes. Actually, I think I have a better. You meant this one.
This
probably,
one,
right?
exactly.
But I have even a better plot, which in my backup. Let me show this to you because I think this is more enlightening. So this is the square root of S, and these are the different channels. So you see here the main one. So pi plus pi minus is the yellow curve that you see here. Right. And pi 0 gamma is this one that you see here. And this is restricted to low energy. So the relevant case, I would say, in order not to have problems with the electrode fit.
Yeah. So at this level, since it is a logarithmic plot,
yes,
is it possible that a 2.5% shift is experimentally possible?
I mean, it's possible, but this is a region where the quoted experimental uncertainty is below 1%. So it's really the crucial region. I mean, let's point out something here, which I think is important and which caught our attention. There are some regions which are not measured, actually. And the regions which are not measured are the hatched ones that you see here. For example, for the pi plus pi minus is this tiny hatched region that you see here in yellow. And for the pi 0 gamma is the big, but big because it's a logarithmic scale, it's not big actually, region that you see extending all the way up to about almost 600 MeV. So first thing we thought is maybe there could be an increase in these regions, which in fact are not measured. This is chi-pt, what is used to obtain this. But actually, the overall contribution of this gray hatched region is just roughly 1 in 10 to the minus 11. So, I mean, it would be an enormous change here, definitely not possible. And for the pi plus pi minus, this tiny strip that you see here, it's 10. Okay, it's 10 because it's a log scale. So of course, this is much higher than this. This is 10 in 10 to the minus 11, which again is very small compared to the discrepancy, which is 250 with the experiment. If I remember correctly, the discrepancy with between lattice and dispersive is about 150 in 10 to the minus 11, which is still you see, certainly much bigger than the 10 that you see here. So it's a bit difficult to make some strong statements with the comparison of E plus E minus and lattice, because lattice is a bit in the middle. And therefore, what I said earlier, which is strong for the comparison with the G minus 2 experiment, cannot have the same strength when I compare with lattice.
Nevertheless, the tension is very real in the sense that you can't get 150 out of these hatched regions.
No, that's for sure. That's for sure.
To that extent, if either, so if let's assume that lattice is correct, and these hatched regions are correct, so then what is going on? So you still need new physics?
That's really a good question that we are in fact asking ourselves, and we in fact don't know the answer. But it's really a very good question. Is there new physics in E plus E minus into hadrons? What's going on there? I don't know. Okay. Yeah, it's a very good point. Very good point.
Thank you very much.
No, thank you.
Thank you. More questions for Massimo?
If actually nobody is asking, I have one more.
Please go ahead.
No, I think my question now is to your very marvelous Muoni suggestion. It's not completely independent in the sense that you are actually taking from that peak onwards 13% from somewhere else.
That is true.
So in that sense, would you be back to the same situation and it say that when you want to make a dispersive versus lattice that you will not have a conclusive answer?
Well, no, but when we have a discrepancy, we have a discrepancy overall. This is a discrepancy. I have not, I do not have the calculation, the dispersive calculation of this region. And it's a good thing that I could try to see to answer your question that I don't know. But your question prompts me this question. What is the difference of this region computed from time-like data and from lattice? Because from the lattice, we have the numbers obtained by these people, and with an uncertainty which is already sufficient for the final goal. So it's really not a problem, this. They computed it 2 years ago.
Okay.
As an exercise, because for them, this region was not particularly difficult. You see, for the lattice, there is really a complementarity with Muoni. So to answer your question, no, I really don't think we will have a problem of the type you're saying, because this is a completely alternative way. And yes, we have a small region, but this small region, which is roughly 10%, will have an uncertainty of what, 1%? So, I mean, therefore, no, it cannot be. It would be 1 per mil. So definitely not going to be an issue. On the other hand, one thing which is important to notice is that our Muoni result, if we manage to obtain it, integrating this curve, this will be completely alternative to the time-like method, because you can only compare two integrals and two integrated results. On the other hand, with respect to our friends in doing lattice calculation, there we could have a comparison point by point, because what the lattice people are doing is exactly this integral. They are doing in Euclidean space. They are doing at negative q squared. They are doing a loop. So that's what they are doing. So really, with the lattice colleagues, we could compare not just the integral, as we could do for the time-like dispersive approach, but even just points, directly points on this curve, right, which I think it will be very interesting. And in particular, it could be also amenable to some complementarity. For example, if some region is easier on the lattice, say in this region here, while we probably will be able to go down in energy here, where the lattice will be difficult. So I think there will be a lot of complementarity between these two approaches.
Very interesting.
But it's a good point what you say. However, no, I really don't think that the issue of missing this part will become a problem. No.
Okay. Thank you. Look forward to the results. It looks
it will take some time, but we hope to get there.
Very exciting. Thank you.
Thank you.
Okay, more questions?
Hello?
Yes,
Yeah.
Jans, go ahead.
Yeah. So I had a question, like what exactly you mean is that there can be undetermined contribution to the experimental cross-section for the hadronic contribution?
What do you mean by having, sorry?
Sorry, like you said that there can be undetermined contribution to the hadronic cross-section, which would affect physics. So what exactly could this undetermined contribution be?
This I don't know. I mean, it's a possibility when we claim that we take as an hypothesis that there is a problem, that the discrepancy has its origin in the hadronic cross-section. Then we realize immediately that in order to solve the discrepancy between the experimental measurement of the mu G-2 and the theoretical prediction, what you need is an increase of the hadronic cross-section. So why there would be this increase, I have no idea, but we are assuming this possibility. It could be, for example, that there is a missing contribution. This is a possibility. Or simply, otherwise, that there is a mistake. Also, a possibility is that there is perhaps, I very much doubt that, but imagine that there is a mistake, some kind of mistake in a certain region, and then tomorrow some experimental collaboration comes and says, look, in that region we had an increase, we did it incorrectly, and we have to increase our result by certain amount. And that's, of course, increasing will go in the direction of solving the discrepancy between theory and G-2 experiment. So why there would be a missing contribution or a mistake, I don't know. We are just taking this possibility seriously and seeing which consequences this would have.
Thank you.
Did I answer your question?
Yes, thank you.
Okay.
Thank you. Other questions? I cannot see. You can also use the raise hand option if you want to ask questions.
I think there was maybe on the chat. I don't know. I see something on the chat. No, that's you. Okay, sure. That's okay, sure. Saying to use the raise hand.
Yeah. Okay. I could not see anything. So maybe I would send you an email to maybe request for the slides at some point.
Sure. Of course. Of course.
Hello.
Yes, absolutely.
Is it too much to ask another question?
Fine with me, of course. If we have
there is an anomaly in RK which actually requires a leptoquark.
Yeah.
So will a leptoquark help in explaining this difference?
I'm not really an expert on this, so I cannot really say. But
hello, am I connected? Yeah. Okay. Sorry.
No, please. But I'm sure that in the audience there are experts that can answer that. Maybe Onjin wants to comment on this, or
Hi. Okay. If we have no other questions, I would like to thank. I would like to thank you. I would also like to thank Manoj for helping me to contact you and for this wonderful talk you gave to us. Hopefully, we'll be able to host you some point physically, maybe in a year or two. So yeah, thank you very much, and we conclude the session here then.
Thank you very much. It has been a pleasure, and I would love to accept your invitation to come to Bhopal when it will be possible. Thank you.
You have our open invitation. It's just we are waiting for the Corona situation to become normal.
Wonderful, wonderful. Thank you very much. I would be very, very happy. Okay. Thank you. Bye, everyone.
Bye. Thank you.
Bye-bye.
Bye, Massimo.
Bye, Onjin. Bye-bye.
Hey, have a good day.
Hope to see you soon. Bye-bye.
Yeah, sure.
Bye, Priyotosh. Bye-bye.